A very good morning to everybody, ladies and gentlemen. Welcome to the next day of Cisco Live in San Diego. I'm so happy to see that so many of you are still die-hard fans of classical routing and networks despite all the SD and stuff. My name's Peter, and probably you are by this time asking, what is this manager going to do with my EIGRP? Well, just a month ago, I was still a tech engineer, and even before that, I had my hands and my contacts with EIGRP for quite some time. In fact, in my previous work, a group of my students, as I used to teach at the university, created what could be called the first world's ever open source EIGRP implementation. So I kind of have my attraction to this protocol, and I would like to share what I know about it with you so that you are empowered to run it and you are empowered to troubleshoot it. If there will be any questions during the session, please raise your hand and shout. I'll be very happy to answer anything that comes my way, though if we feel like we're running out of time, I may also ask you to postpone the questions after the session. And of course, we have the WebEx Teams room where you can ask questions, so we'll also make use of this. I would like in this session to touch the following functional areas of EIGRP where you may face problems, which is technically troubleshooting toolkit that we can use to peek into the EIGRP operations and see what's going in there, and then start looking at different functional areas, establishing adjacencies, exchanging routes, selecting best paths, advertising that information, and we'll also look at a couple of specific functions and specific features in EIGRP that might have come lately, and which may pose specific challenges to your network. With it being said, let's get started. I'd like to talk first a little about the toolkit that you can use, though I won't be dwelling too much on commands because it's kind of dry. And most of you even know about those, so I just want to highlight what's available and also highlight maybe some of those tasks and tools that might come handy if you're not using them too often. Before I start, though, there is one thing I always like to do at this session. Start from a slightly more general point of view and talk a little about what troubleshooting is really. Troubleshooting typically starts when the system you're looking at, maybe the EIGRP or anything else, doesn't behave the way you expected. Like the bloody thing is doing something you don't want it to, or, you know. Now, troubleshooting can be seen as an activity to minimize the gap between what you expect the system to do and what it is really doing. But you know, we can approach it from both ends. Fixing the real problem, if there is any, or also improving our understanding. And I'm talking about this because EIGRP has been kind of an engineer's pet, to be honest. It was an in-house protocol. It has been improved, extended, embellished, added with new features, so some of the things are not really well described or some of them are non-intuitive. So in this session, I will also be talking about some of the topics and some of the features that EIGRP has that are maybe even discussed outside but typically understood wrong. All right. What are the possible areas where EIGRP can screw up? Well, first of all is we may have problems with adjacencies. We don't even establish neighborships between myself and my neighboring router. Or if we establish it, we have problems exchanging the set of routes I know and what my neighbor knows. OK, I may have exchanged it, but then I perform the route path selection. I decide what is the best path. And I decide it somehow unexpectedly, or maybe the route doesn't make it into the routing table. The question is why? Furthermore, when I've decided what is the best path, I need to tell my neighbors so they also know. OK, did I? There can have been a problem. And finally, we need to be aware that anything that changes in the network also has to be taken into account. We need to stay on top of our game. We need to stay on top of the topology and its state and advertise anything that changes. And again, there might be issues with this. So we can split everything that happens in EIGRP into these areas, and this is what I will be looking into over the next 2 hours. What can we use? Obviously. There's a bunch of show commands across all our platforms, typically the most ones used. There are available event histories. iOS isn't that great. Who uses NX-OS and Nexus switches, you know that the event histories on NX-OS are far superior to iOS and allow us better looking into the past and what was happening. If situation starts getting really serious, we can do debugs. And of course, packet captures. They're also very useful. So let's go and see what we can use in this toolkit. For iOS and iOS-XR, the show commands typically start with show IP EIGRP. If you're bold enough, show IPv6 EIGRP. Or if you're using the named mode, it will be show EIGRP address family something. You know that these variants are largely equivalent. For the sake of brevity, I'll be using the short versions in this session, just show IP EIGRP, but all of them are equivalent. Aside from this, if we need to do if we need to look into the event histories, we also keep an event history in iOS that typically has 500 lines, and I'll be talking about it in a moment. If you're happy enough to run iOS-XR, and if you need to capture traffic in EIGRP and see what the communication looks like, you can use embedded packet capture. Who knows embedded packet capture? Hands up, please. A couple of you. OK. Embedded packet capture on iOS-XR platforms allows you to capture all the traffic that goes into your supervisor on your CPU or out of it and store it into a file or display it on your command line, CLI. And then, especially if you save it, you are able then to analyze it in Wireshark for further information. This is very useful because if you know and see what your router is really telling your neighbor, you can start troubleshooting from that. If the situation gets really complicated, you may need to resort into debugs because they, on iOS platforms, they are the only ones that give you detailed insight. You know that debugs are always a sensitive stuff. And if you need to do them, be careful. Turn off the console logging. Don't let the outputs go to the console because that's processor heavy, lots of interrupts. And rather, redirect them into the buffer logging or go ahead and store them right into the file using the log file. Do not have them going to the console, never. With the event log I've mentioned, the event log is on by default since about 12.2 iOS version. This event log stores some of the events that EIGRP has been going through. And by default, it's 500 text lines that we maintain there. It can be tuned using the command of EIGRP event log size. Of course, it can be cleared. And typically, when you display it, it goes from the most recent events down to the least recent, kind of similar to what NX-OS on Nexuses does too. This is there for you. And aside, and as opposed to the debugs, event logs do not consume too much CPU, so they are your friend. We'll be looking at some of those outputs later. For NX-OS, well, if you run EIGRP on NX-OS, we have very powerful event history logging that you know typically start with show EIGRP internal event history and then something, and there's a lot of commands that you can look inside. And many, many commands are of the same stuff. Interpreting those outputs may be slightly challenging since they are kind of technical and more about for tech people, but still you can get a glimpse and an idea of what events have been going in and out from the EIGRP system and have an idea what the EIGRP was doing at the time. If you needed to capture traffic under NX-OS, you can use Ethanalyzer. Again, please, hands up. Who knows Ethanalyzer on Nexus switches? Oh, just so few people. Ethanalyzer is literally text version of Wireshark embedded into NX-OS. And I mean it. It's really the Wireshark code retaken into NX-OS and enabled as the Ethanalyzer command that is available for everybody who is in the VDC, actually no network admin user role. Again, it allows you to see everything, every traffic that goes into your supervisor or leaves it. It's not for transit traffic. You won't affect your transit traffic. But you can see what you are sending as a switch, as a host, or what you are receiving. And again, you can either display it, filter it, or save it to a file and then run real Wireshark on top of it. Very, very useful. If debugs are needed, they are still available even on NX-OS platform, but typically you don't need to resort to them. And again, if you do need them, again, no logging console and logging log file is your friend. Again, don't let the logs go to the console. Never. That's a rule. These would be the tools that we typically have available, and I will be using these for the rest of the session. So let's start looking at the problems we may see in the EIGRP now, really. So looking at the first area that we may have problems in is establishing adjacencies. EIGRP has three main tables that it maintains. It's an interface table, neighbor table, topology table. These are, again, your very big friends because they link to each other and they say what EIGRP is operating on. If you don't have an interface in the interface table, you cannot establish an adjacency with somebody else on that interface. If you do have an interface in the interface table, but you don't see a neighbor across that interface in the neighbor table, you cannot exchange routes with it. And finally, even if you have a neighbor known, but if you do not learn some routes from it into your own topology table, you cannot advertise it further. You cannot install it into your own routing table. These are your friends, and these will be the most visited data structures in EIGRP that we have. As you know, EIGRP detects neighbors dynamically, and that's done using multicast hello packets. We can also specify neighbors statically, but typically this is not done. EIGRP neighbors have to meet a several set of conditions that allow them to become neighbors. If some of the parameters do not fit, you don't become neighbors. Which are they? Again, what does need to match between two neighbors? Just shout. K-values, wonderful, that's one of the things. AS neighbor, AS process number, right? Timers don't need to match. Actually, OSP is the only one that asks you for that. EIGRP is flexible. ASN, the autonomous system number. Anything else? Subnet, yes, you must be on the common subnet. Anything else? If you're using authentication, then obviously authentication has to match. All these, perfect, all these things need to match. We need to have the same autonomous number or the process ID. We need to be on the common subnet on non-passive interfaces. There is one exception to this. Anybody? Unnumbered, exactly. For unnumbered, you really cannot be on the same subnet. Use the same k-values to compute the metric in the same way, and use the same authentication parameters. If anything of this, any single one doesn't match, you won't be friend with your physical neighbor because there is a mismatch. Now, I would like to peek a little into how EIGRP truly established the adjacencies between two routers, because there's, again, some useful information we can use when troubleshooting these problems. And if everything starts with hello packets, and let's say in this example, it's R1 that first sends a hello onto the multicast segment, and R2 receives it. What happens? R2 recognizes that there is R1, hey, I have a new neighbor, and puts it into a state that we call the pending state. In the pending state, we know that we can hear him, but we don't know if he can hear us. So we do not exchange routes with that neighbor right away. We need to verify the bidirectional visibility. That's why I say that it's a pending state, and we are waiting for the initial packet from the neighbor. And when we send our own initial packet to the neighbor, we expect the acknowledgement to come back. That's why we say we wait for init and init egg. Of course, this happens in the opposite direction too. R2 sends a hello packet. It goes to R1. R1 creates an entry. It just learned about the new neighbor. And it puts R2 into the pending state as well. Again, waiting for init and init egg. When I say init, it's just a flag in the EIGRP header that tells us we're starting anew. But we need to know that we haven't missed anything. We need to know this is the real start. Now what happens? Let's assume, for the sake of discussion, that it's the R2 that first sends this initial packet. The initial packet is just an empty update. We call it a null update because it doesn't have a body. It just has a header. And in this header, we have the init flag set and the sequence number R2 is currently using. So far, so good. If this packet makes it, too far, then R1 is happy because it just has received an init that was expected from R2. It's just waiting for the init acknowledgement, but it will send its own null update with its own sequence number and also with the acknowledgement number acknowledging that R2's own null update has been received. At this state, R2 is very happy because it has received both the initial packet from R1, which was expected, and acknowledgement combined in this update of its own null update. So R2 is now happy. It knows that R1 understands it, can hear it, and puts R1 into the up state. We just need to acknowledge R1's own update, which we do with a normal just acknowledgement, and done. When this is received, R1 also comes up, declares R2 to be up, and then we got the ball rolling and we can exchange the topology table contents. This sequence here in the middle, it's very similar to TCP three-way handshake, really, like SYN, SYN, ACK. So nothing that special. Keep in mind these names, waiting for init, waiting for init ACK, because these will be indications in the neighbor table if something goes wrong, and we know then what goes wrong. All right. OK, if I asked who hasn't seen this output, I hope nobody would be raising hand by this point. Everybody knows the neighbor table, and I'm not going to talk about the obvious columns. Just want to mention a couple of details here. The smooth route trip time and route trip retransmit timeout, the RTO columns, they are there to know how long it takes for the neighbor to respond. We use it to pace our packets and pace our retransmissions. These will only be updated when you exchange the packets we call reliable packets, those that need to be acknowledged. If your network is stable and you don't send any new updates, new queries, new replies, these numbers here won't change. So they may even be at an unrealistically high numbers because your network has just come up. We start with very conservative numbers, and we tweak them down as we exchange updates. But if there are no updates, they may stay high. That's not a problem. If you send a new update, they will get tuned. But don't worry if they initially are up. That's not a problem. However, the queue count, this is very important and probably most important column here. Anybody, what is the queue count? Updates waiting to be more than that, not just sent. Acknowledged, acknowledged. Whenever I send an update or a query or a reply to somebody, I need the guy to acknowledge it back. If he doesn't, I send it again. Well, if there are outstanding packets sent out but not acknowledged, I might have a problem because the acknowledgement is not coming back. My update isn't making it through. In the stable state of your network, queue count must be 0. Must be 0. During reconvergence, that's normal. You may see a couple of seconds to having non-zero numbers there. But if your network is truly stable, nothing's changed, it should be converged, you must not have anything else than 0 in this column. If you do, you have a communication problem. And finally, the sequence numbers. As you know, EIGRP doesn't have sequence numbers for its reliable transport protocol on a session basis or an adjacency basis, but rather just on a per process basis. If it's increasing, that neighbor is sending updates. What's the normal rate of sending updates? I don't know. This is totally about your baseline. So it's up to you to understand if a certain rate of updates is normal or not. Just be aware if it keeps increasing, you're updating something. Something's happening. EIGRP is working on something. So it's an indication, an indirect indication of some activity in EIGRP. What can go wrong with EIGRP adjacencies? Let's have a look here. One of the typical problems that happens is you see an adjacency that doesn't even come up, or comes up but then goes down and maybe even flaps repeatedly. And with even reasonable recent code, you will get a message in your logs saying that the neighbor has gone down because, and now it comes. Peer graceful restart. I suppose you have seen this quite often. Neighbor down because of graceful restart typically happens when you change a configuration on the neighbor that requires it to resend and re-receive the routes between the neighbors. Like you apply an offset list, you apply distribute list, you change next hop self, you may change the split horizon. All these changes will cause the neighbors to resynchronize but not tear off the adjacency completely. So this would be the graceful restart. also, if you did really do a full reload of the neighboring box, but the box supports non-stop forwarding, then this reload can be also done using the graceful restart feature. Another possibility that you may see is P restarted. Well, this is more serious. This looks like somebody issued clear IP EIGRP neighbor enter. So the process really stopped and started totally anew, not gracefully. Or, for example, if you configure EIGRP stub or remove it, again, the adjacency is torn down completely and then reestablished. Typically, this would be seen as the problem. Or, obviously, you may have reloaded the box very quickly. This is also a possibility. Holding time expired. Well, this is something we don't like to see. Obviously, for the last hold time seconds, we haven't received any valid EIGRP packet from the neighbor. So this connectivity issue. This is even more bad. Because we are trying to get a message across to the neighbor, and it doesn't just get it, because we are not receiving an acknowledgement. So we repeat it, we try 16 times, then give up. And this is when it comes. Retrial limit exceeded. And finally, interface peer termination, or sometimes in older code, interface goodbye received. Anyone what this might be, or what this is good for? Interface goodbye received. For example, if you shut down an SVI, or if you shut down the whole EIGRP process, typically for your neighbors, it would take 15 seconds by default to understand you're down. If you want them to know upfront that you're leaving, you can send them a goodbye message, which is really a hello with all K values sent to 255. And the neighbor knows that you're essentially leaving immediately and doesn't wait for the whole time, reconverges right now. It's a way of informing others that you're vacating the slot. What are the typical causes of EIGRP problems? Well, the typical with mismatched configuration parameters, we typically see the neighbors not even coming up. Sometimes we log a message, but typically it's just silent and we don't see the neighbors at all. What to check if you have these symptoms? You do not even see the neighbor coming up on neither side. Check the parameters that are mandatory to be the same. I won't repeat them for brevity purposes. Show IP EIGRP interface is your next friend. If the parameters between you and the neighbor seem to be okay, check if the interface to the neighbor is visible in the show IP EIGRP interface output. Passive interfaces will not show up, and also interfaces not covered by network command will not show up. And such an interface obviously cannot establish adjacencies. So again, if an interface is missing from the interface table, well, we need to get it there before we can establish any adjacencies. If it's there, then let's try testing the connectivity. Try pinging both the unicast address of your neighbor to see if it talks to you. And also, this is not done often, but should be done. Try pinging the multicast IP address. Because if the multicast is working, then the neighbor should respond when you ping the multicast the EIGRP address. And again, take it from there, because now we would start troubleshooting not really EIGRP, but the underlying unicast or multicast connectivity. But it's your good friend to narrow down just where the problem might be. With certain situations, we see that the unicast and multicast connectivity may be broken in such a way that unicast works, multicast doesn't, or vice versa. Especially if you think about the stretched VLAN technologies like OTV, Fabric Path, VXLAN, EVPN, where we do tricks on stretching the VLANs and handle, especially multicast specifically, we may see that unicast is working, but multicast is broken, for example. Typically, this exhibits itself as the neighbors coming up but then falling, and sometimes they both come up and then go down, or just one of them comes up, the other one doesn't even show any new neighbor. It just comes up and down on one end, and the other one doesn't see anything. What would you typically see in show IP EIGRP neighbor detail in this case is an information that you are trying to do this initial synchronization with the neighbor, but it's probably failing. And this is the waiting for init and waiting for init egg. This situation means I know that it exists because I've received a multicast hello from him. That's why I have him here in the first place. But now I'm waiting for this null update to come from him. Not coming. Let's wait for init. And I've sent my null update to him, but no acknowledgement has come back. That's why waiting for init-ec. This helps you to narrow down just what's happening. Remember, the synchronization is unicast. So if I see these problems, I've got a problem with unicast connectivity. The fact that the neighbor is even here, that's thanks to multicast hello. So multicast, at least from him to me, seems to be working. It's about putting things into perspective. What you should be checking in this case, check the input ACLs on the interfaces, because it's so easy to forget that EIGRP is not fully multicast based. It also uses unicast. So if you do ACLs, keep in mind that you need to allow EIGRP both for multicast and unicast communication. Also, I've seen situations where there was a static net configured for some kind of internal IP address, statically netting that internal IP address to the IP address of the outside interface, one-to-one. And that outside interface was also running EIGRP to the upstream router. Now, when those init updates, init packets, null updates, came in, they are unicast, they were coming to the outside IP address. Well, net acted, translated those EIGRP packets into the inside IP address because there was this static net, it was unspecific, and send those EIGRP in. So the initial sequence exchange could never be completed. It's a weird thing, but it happens sometimes. So be mindful of it. This is actually quite nasty to troubleshoot. Again, try pinging, if this doesn't help, try pinging the neighbor and try pinging the multicast address. If the neighbor responds on unicast, you need to check what's happening with the multicast. And this is an area in itself. Typically, you may have overzealous IGMP snooping switches that don't understand that this IP address should be exempted from IGMP snooping and allowed to be just flooded. There may be issues if you have VXLAN or OTV. There might be issues with handling the replication in the underlay, so this will need to be troubleshot explicitly. If multicast works but unicast ping doesn't, then it's about troubleshooting the unicast connectivity again. Though, keep one thing in mind. To have unicast working, you do still rely on broadcast for ARP or multicast for IPv6 neighbor discovery. Sometimes the broadcast multicast is broken, and that's why you cannot get a resolution from the IP to the MAC, and so the initial exchange fails. So try configuring static mappings for ARP or ND and see if the adjacency comes up. Because again, then you know that it's something just with the what we call the BUM traffic, broadcast, unknown unicast, multicast, and troubleshoot that, or ask it to help you. Hands up, please, who is lucky enough to be using Nexuses and VPC in your topologies? Okay. My sympathies. For those who do not use the virtual port channel, just a quick introduction. The virtual port channel is a technology that tries to emulate a single switch out of two independent boxes while keeping their configurations and their data and control and management planes intact and independent. We do this by pretending that we have the same bridge ID in STP, the same system ID in LACP, but otherwise, those two switches keep their independent routing tables, different IP addresses, and stuff. The VPC domain, as we call it, one virtual switch consists of two physical nexus switches and a special link between them, which is called the P-link. The P-link is just the trunk that carries both a normal traffic plus some synchronization information between the two guys so that they can share, for example, their MAC address tables. And there is a very specific rule here to prevent switching loops and frame duplication. If I, as a switch in the topology, the one of the members of the VPC domain, receive a frame through the P-link, I am not allowed to send it through any virtual port channel. Think here. The router at the bottom may send some kind of a broadcast or something. If I was handling the broadcast in the totally classic way, the broadcast would go, well, where? Everywhere. It would go up to the switch on the top, and it would go to the switch on the left, right? And if the switch on the left did the same thing, it would flood the frame again. So the frame would go, again, both to the top switch and back to the original router. If this was not protected by the loop prevention rule in VPC. So this is why I have this rule. We cannot forward or flood a frame that has been received through a P-link through any virtual port channel to avoid frame duplication and possible switching loops. But what can happen here? Imagine the router at the bottom needs to talk to the host 2222 somewhere in the top. And the router at the bottom is also configured with a default gateway, which is the left switch, 1111. So far, so good. So the router creates a packet, puts it into the frame. The destination of the frame will be the left switch, switch A, because that translates to the IP address 1111. But because of the hashing on the Ether channel, we put the frame onto the link to the right switch, the switch B. What is the switch B going to do? Well, the destination MAC address is not its own, so it needs to switch it. We switch it through the P-link. It goes to switch A. Again, so far, so good. Now, the destination is switch A. It unpacks the packet, should route it, should forward it. Do you think this happens? Well, by theory, it should, because we're forwarding packets, not frames. Well, for the sake of performance efficiency, we don't really make it in such nice boxes as the OSI model wants to do. We do the switching and routing in one go, and we forget. We don't care that we actually routed the packet. We care only about one thing. Did it come through P-link? Can't make it. So in this situation, if this ever happened, your routed packet from the router on the bottom would never make it to the switch on the top. Because the VPC prevention rule kicks in, it doesn't take VLAN boundaries and routing into account. Simply, it's very, very statically imposed. What do we do then? We use a feature that is called a peer gateway. Peer gateway technically means very simple thing. Those two switches that form the VPC domain share their MAC addresses mutually. The switch on the left keeps its own MAC address and adopts the MAC address of its peer on the right. The switch on the right keeps its own MAC address and also adopts the MAC address of the switch on the left. As easy as that. And now when that happens, and I repeat the scenario, router at the bottom sending a packet to somebody on the top, switch 2222, yes, the destination MAC is initially owned by the switch A, but is also adopted by the switch B. So now when the frame hits switch B, we just unpick it and route it because we handle that MAC address as well. That's what the peer gateway does. And that's what you should be using, in fact, because otherwise you end up in weird problems. OK, fair enough. But now imagine you want to have an IGP adjacency, OSPF, EIGRP, over the same setup that we have with peer gateway already in place. So what happens? Router at the bottom is sending, let's say, this null update packet to switch A, and again, because I'm mean, I am having the frame go to the switch B instead of switch A directly. What happens now? Since we have the peer gateway, the MAC address is shared. So switch B doesn't just switch the frame, it consumes it. It looks into it because it thinks, yeah, it's mine. Finds the packet inside, but the destination IP of the packet doesn't belong to switch B, it belongs to switch A. So what do? We route it, of course. We make a forwarding decision based on the destination IP address. But when we route, we decrease TTL. If we decrease TTL, we may hit a problem if the initial TTL of the packet was already 1, which it was, or if we are using what we call the general TTL security mechanism, that you send packets with a TTL of 255 and you expect them to arrive at 255 because they will arrive at 254. This behavior will break your adjacencies in any IP-based IGP, OSPF, EIGRP, well, even RIP, if you're using it. And it's going to show up as this kind of broken connectivity when multicast makes it and unicast doesn't, because you cannot get your unicast packets across this routed thing. So what do we do in these situations? We need to use additional configuration knob, which is called the layer 3 peer router. And this knob stops decrementing the TTL of the packets that get routed across the peer link. We don't touch it. We still see lots of cases coming into tech where customers are not aware of these intricacies. And they replace catalysts with nexuses, and suddenly the nexuses don't establish the adjacencies. It's flapping all the time. Typically, they forget to use the layer 3 peer router functionality. Keep this in mind, please, because yeah, it may hit you badly. One thing. If you've been using iOS pre-15.12, and if you still have been successful in establishing adjacency through VPC, that might have been because we have been kind of lousy. In the iOS, we have been sending EIGRP packets with a TTL of 2 instead of 1. Honestly, I do not exactly know why. I suspect it has something to do with the very, very ancient deployments in frame relay, where you typically also, if you wanted to have spoke-to-spoke communication, you also needed to go through the hub. Ribos behaving the same way. Starting with 15.2, we've changed it, and the TTL is 1. So pre-15.2 iOSs just work, even through VPC without any additional config. 15.2 and more, they stop. Unfortunately, not described anywhere. Sorry for that. All right. Let's move on really quick. Other problems that you may be seeing that also may influence your initial establishing of the adjacencies. Combination of static and dynamic neighbors on an interface. This doesn't work. It's simply not supported. Either all neighbors are static or none of them is. Because if you remember, the neighbor command in EIGRP also takes as a parameter the name of the interface. It disables the use of multicast on that interface completely. You don't send anything as multicast for EIGRP. You ignore any EIGRP multicast. You simply don't listen to that address. You cannot combine static and dynamic neighbors. Unidirectional links, that's another problem which typically cannot be solved by configuration, but rather by fixing the link itself. Or the underlay, if it's again some kind of an emulated circuit, emulating E-line or something. Just be mindful of this. Or, well, this would be something either a very bad misconfiguration or somebody pulling a bad prank on you, setting the whole timer shorter than your hello timer. It's still possible. Yeah, we truly allow you to configure things your way, right? All right. Finally, packet losses, control plane policing kicking in, physical layer errors. All this can come and bite you, but this has to be taken into account in a particular network and look into context. Let's see about the initial neighbor synchronization, what can go wrong. So let's assume that we have the neighbors coming up and running. They're fine, they're good, but something gets wrong. What happens is that once the EIGRP comes up between the two neighbors, they try to send all best routes they know in the topology table to each other. Now, be mindful that if you check the topology table later, we actually use the split horizon, and we advertise routes toward our own next hops as unreachable. So if on that next hop, you go and do show IP EIGRP topology or links, you may not see all neighbors advertising all routes. Even though we don't have any filtering. You might ask, why don't I see that neighbor advertising the route to me back? It might be simply because of split horizon, because you are its own next hop. That's all good. Size of the topology table matters because we try to exchange it all, and we do not rely on IP fragmentation. We try to split all the entries into IP packets sized based on the outgoing interface's MTU ourselves in the EIGRP code. And this immediately leads us to the major Number one root cause for troubles in the initial in synchronization problems, MTU issues. If you have a different MTU than your neighbor and you have lots and lots of networks to exchange, you may face a problem in that you can fit them all into a large packet, but that large packet, if your neighbor has a smaller MTU, will not be accepted as valid. Typically, this means that the EIGRP adjacency comes up and is okay, but then we cannot conclude the initial synchronization. And if you do, again, show IP EIGRP neighbor detail, you will see no longer waiting for init and waiting for init egg, but rather an update, sequenced update, standing there and being unable to be acknowledged because it doesn't really make to the other end. MTU issues cannot be worked around in EIGRP. There is no knob similar to IP OSPF MTU ignore. You simply have to make the MTUs the same on both ends. Might be challenging, but this is the only way to make this work. What else? Be mindful of EIGRP packet pacing. You know that EIGRP tries to use the bandwidth sensibly on an interface, but at the same time, it's allowed to go by default to up to 50%. 50% of the bandwidth of the interface that you either configure or if you don't touch it, then it's going to be the value simply derived from the momentary operational speed of the interface, at least on Ethernet. Now, if you start getting creative with the bandwidth command, you may end up in a situation where the bandwidth is either unrealistically high, meaning that you, even half of it, may oversubscribe the physical interface and you will get packet losses. Or, if you try to make the link very unfeasible, you may have made the bandwidth very small. And in that case, you're throttling down EIGRP too much, and it's very slow in exchanging the updates. You maybe remember that in old codes, the tunnel interfaces, for example, had the bandwidth just to 9 kilobits per second. That's ridiculously small. So the takeaway from this is keep the bandwidth at a realistic value, and most certainly do not use it to influence EIGRP's best path selection. Use the delay for that all the way. OK. Any questions so far? OK, let's move forward. Let's look at the best path selection in EIGRP. And because EIGRP happens to be using quite an arcane terminology, I would like to run through a couple of terms here. Don't want to bore you with it, but there are some things that may be new to you. OK. Everybody heard, I suppose, about the reported distance in EIGRP, really, right? That's my neighbor's distance to the destination, as he tells me. If I was just looking to this topology and looking on the path from router A to router E, from all the top down to the all bottom, then my neighbors, as seen from router A, are B, C, and D, and their own distances reported to A would be 10 for B, 10 for C, and 30 for D. These are the reported distances. In the past, we have also called them advertised distances, but because the acronym also overlaps administrative distance, we've stopped using that. That's better this way. When A decides to pick the best path, obviously it needs to take its neighbor's distance, the reported distance, and add the cost of the link between A and that neighbor to arrive at the complete cost to reach the destination. And this actually has a name. We call it computed distance, although we don't typically show it anywhere in the outputs. But for example, the SNMP MIP for EIGRP has this name. So in total, it would be 20 through B, 25 through C, and 45 through D. And this would be the computed distance. Again, no rocket science here, just good. Feasible distance is typically something that gets wrong. Feasible distance is not your best distance to the destination. Feasible distance is a record of how close you ever have been to the destination. Not momentarily, but sometimes in the past. And the past starts, again, with the diffusing computation. So really, what feasible distance truly is the historically smallest distance to the destination since the last time you've concluded the diffusing computation and went from active to passive state. You may be asking, why is this? Because it's used in the feasibility condition, and I'll show you later how this behavior works. just keep in mind this. Your feasible distance may not be the same as your current best distance, may be different, maybe lower. And it's never sent to anybody, never, in no packet. It's a purely local value. You do not exchange with anybody. Let's take this network here, and let's just focus on the path from A to E through B. Let's assume that this is the starting state of the network. This is where we started. Since we've just started, there was no past history. Yeah, my best distance is 20, and so will be the feasible distance. So far, so good. Now let's assume that the link between A and B got slightly more pricey. It gets to 15. Yeah. So my best distance is now 25, and actually in this network, I would be using both B and C as my next hops. The feasible distance stayed at 20. It's not 25, it's 20. Historical minimum. And then later, let's say the link gets cheaper, even cheaper than before. Now it's even 8 units. So the total cost is now just 18, and so will be the feasible distance because we hit a new minimum. This is how it behaves. Okay. The only way to increase that cost is only to do an active diffusing computation. No other way of increasing the feasible distance. And now how is this used? Why is this way? Well, we have this marvelous condition we call the feasibility condition that is used to verify if a neighbor provides a loop-free path. Any path selection in EIGRP go through this selection and go through this test. And you know the formal definition that if my neighbor's reported distance is smaller than my feasibility, to me, it doesn't mean anything. I cannot actually visualize this. So let's put it in nicer words, right? If you are to the destination closer than I have ever been, you cannot form a routing loop through me. This is really what the feasibility condition tells you. If you are closer than I have ever been, and why this works? Because if you are closer, I don't care if you know that I might have just learned about an update. You haven't used me in the past because your distance is smaller than what I have ever been. If you have used me in the past, your distance would be at least mine or maybe even bigger. So you haven't used me any time in the past. And even less you will use me if you find out that my distance has gone even higher. This is the loop-free property that the EIGRP really stands on. Be mindful of this because it also tells you about something about feasible successors and stuff. Now, tying into the topic, you know that neighbors who maintain these properties and satisfy the feasibility conditions have two names, feasible successor and successor. Very quick, feasible successor is anybody passing the feasibility condition. Anybody. Successor is somebody who is not just loop-free, meaning he is a feasible successor, but also provides the best momentary distance. Because you want to always use the shortest path, so use the successors. Feasible successors can be used as backups. That's also how they are intended to be used. Okay, fine. In this network, B is a successor. C is a feasible successor. It's still loop-free, but isn't really as good as B. And D is nothing, because it doesn't fit the feasibility condition. It's not really looping, but we cannot tell just by looking at the distances. So we don't take chances. That's the whole point. So we typically call the router D a possible successor, but it's kind of an unofficial name. Let me, however, change the metrics a little. What I've changed is the links between A and D, and then D and E. Now, if you think about it and look closely, the best path is through B for 20. Then we have a path through C, which is for 25. But because C reports distance of 10, while again, I'm assuming they've just started, my best distance is, and also the feasible distance is 20, C passes. His 10 is smaller than my 20. And then we have router D. The total metric through D is 21, better than through C. but D doesn't pass the feasibility condition because his 20 is not strictly smaller than my 20. So D isn't really anything in this network. Now my question is, what happens if router B fails? The textbooks will tell you, yeah, you just start using the feasible successor, you have it, C. No, you won't. Because if you did, you would be stuck on using loop-free path, fair enough, but not the shortest one available. Here's what happens really. So B fails. B is down. A runs through the topology table and checks the remaining neighbors and their distances. It finds that the neighbor providing the next smallest distance is D. That's right. And then it checks if D passes the feasibility condition. And the answer is no, it doesn't. Because the neighbor that provides the least distance in the moment of handling the topology change does not meet the feasibility condition, we must go active to find out if we can use it or not, because we want to be using the shortest path that is available. And so we go active, we send out queries, we ask the neighbors, the remaining neighbors C and D to see if they, how they respond. Since neither C nor D is using A as their next hop, they don't care about A's change distance. So C will repeat, yeah, I'm still for 10 from the network. And D will respond, yeah, I'm still for 20. That's what they're going to say. I don't care about your distance because I'm not using you, Mr. A. That's what's happening. When these replies come back, A can just reset the feasibility condition, reset the feasible distance, and set it to the new minimum, which is 21. So we move from router B as the successor to router D as a successor without ever using router C in this topology. C has been and has remained this topology just a feasible successor. If you were using the LFA extension, loop-free alternate, the fast reroute extension to EIGRP, you would be using C temporarily, but you would still go active because you still want to go for the shortest path that is available. Keep this in mind. It's not true that you would be just jumping on the feasible successor just because it's there. No. I won't bother you with these rules here. I don't want to lose time. The only thing I want you to take away from this is you always look for the shortest distance, just as RIP does, but just before using that neighbor, you also verify if it's loop-free. If it's perfect, go for it. If not, invoke the active state, go for the diffusing computation, and perfect. Then use whatever is left after the diffusing computation. This is the whole idea. Now, this being said, we can look at the topology table and take it apart, because that's where the wisdom is. And again, I cannot stress the importance of the topology table enough. That's the EIGRP's playground. Everything that happens, everything you advertise, everything you learn is there and has to be absolutely perfect. So, Show IP EIGRP topology summary will show you a very quick overview of how many entries you have in the topology table. What you're typically interested in is how many routes you have, how many replies are pending, especially if you're in the active state. You may ignore the dummies. It's just an internal structure that handles the sum of the topology entries that we need to maintain. Also, the quiescent interfaces are those interfaces where there are no outstanding packets to be sent or received. In a stable network, all your EIGRP-enabled interfaces should be here. Again, if some is missing, there's some kind of communication going on. For more details, you typically do show IP EIGRP topology, and as you know, you will get a list of all node networks and their details there. So what do we have there? There is a feasible distance, just one, not for neighbor, just for destination. And then per neighbor entries for those guys that have told us something about the network. And every time you will have the successors listed first, the feasible successors listed second or afterwards. We do not draw a line, however, to indicate which are the feasible successors. They're just there, just sorted by the total distance, the computed distance. In the brackets, The second indicated distance, the smaller one of the two, is the reported distance, the neighbor zone, and this is the computed distance. This is what we have there. You know that we also have this all links switch. If we use the all links switch, then we will see all neighbors that told us about the network, including those ones which are just those possible successors. Again, I remind you, keep in mind that we are running split horizon. So I won't see a route being advertised from somebody who uses me as his next hop. That is normal. That's not a problem. We can also go further, and if we did show IP EIGRP topology and then invoke the specific network, you know, you then get all the vector metrics, as we call them, details for the particular entry with the delay, bandwidth, reliability, load MTU, and other stuff. Everybody knows this, so I'm not going to dwell on this too much. Zero successor routes may be important. The zero successor routes, they are routes that are learned from other EIGRP neighbors but didn't make it into the topology table, sorry, routing table, because the routing table already contains the route from a more trusted routing source. It may be a different protocol whose administrative distance is smaller, or it may be a static route, which again just aligns with the AD. The idea is that if you, as an EIGRP router, cannot install the route into your routing table, you also cannot advertise it further, because you are not using it, so you cannot pretend to others that you are using it. That would lead to routing loops. So zero successor routes will not be advertised to anybody. And once again, they are there because they didn't make it because of a, administrative distance. All right. The first thing to check, if you suspect something wrong here, and you don't see the route being in your routing table, go to the topology table and simply check if it's there. Why would a route not be in the topology table? Can anybody tell me? At all? We can obviously use distribute lists and filter it out. Or maybe your neighbor is a stub, and you know that with stubs we do limited propagation of routes. Or maybe the route has hit the maximum distance as it was advertised across your autonomous system. It hit the maximum, and again, for infinity, it's treated as unreachable. All these things have to be taken into account. And of course, the most simple one, maybe just the network command is being forgotten on the source router that is supposed to be advertising the route. Keep all this in mind when you are looking for the reason why the route is not being even placed into the topology table. If it is in the topology table but doesn't make it into the routing table, check the metric. If the metric is hitting the 4-byte maximum, it will not make it into the routing table because the routing table in iOS only works with 4-byte unsigned integers as metrics, and the maximum integer would also indicate to the RIB manager that the route is not really working. Of course, also make sure that it's not a zero successor route. That one wouldn't make it because of obvious reasons. And show feasibility condition also has to be checked. Regarding the route troubleshooting, the advertisement and convergence issues, let's see, the convergence in EIGRP, you know that we have these local computations and diffusing computations. With the local computation, that means that you can just switch from one neighbor to another because the next neighbor is still satisfying the feasibility condition. That is quick, fast, works quickly. The active computation invokes all the queries and replies, and will need to take more time. And also, it may happen that an unexpected event happened, in which case you need to handle it based on what it actually is. Whether you are going for a local computation or a diffusing computation purely depends on how does the next neighbor providing the next best distance look like in terms of feasibility condition. If we have a local computation, and this is just here as an example in this network, I will be failing the link between B and E. So router A that has formerly been using router B as the next hop will need to flip over. to somebody else. And this network is engineered in such a way that C is the next best one, and also C satisfies the feasibility condition. So when the link between the B and E fails, what I can see is simply A running down the topology table and seeing the C's both meeting the feasibility condition and providing the best distance, so it just moves over. If I looked at the event logs that I just told you about at the beginning, this is what you would see there. This is router A saying what it sees. This find FS means find feasible successor, because B was asking, hey, A, can you tell me another path to E? I've just lost it. And A goes, OK, B, I know that you're not my next hop anymore, but let's see. I know C, and C is passing the feasibility condition. C is providing the next least distance. Perfect. This is my distance. I'm choosing over to C. There is no sending replies, sending queries here. We just see feasibility condition satisfied here. And this is something you would see in your show IP EIGRP event log. For the diffusing computation, seems like this thing has an artificial intelligence. You know, my dad likes to say that the natural stupidity is better than artificial intelligence, and I have to concur. What's happening here, I'm going to remove the link between A and C to also exhibit the possibility for a diffusing computation. And again, I'm going to fail the link between B and E. Now, if B fails, then A cannot converge through C, and since D isn't really passing the feasibility condition, it needs to ask. What you would see in this case, in the show IP EIGRP event, is not only feasibility condition not satisfied, but also active. This active state means, well, you need to go active, you need to start querying, you still not need to start doing things. All right. Any questions so far? OK, everybody, stand up. Stretch yourselves, please. OK, you can take a rest again. Stuck inactive. Who was bit by this? Yeah, it's a very pitiful situation to get solved, right? Let me talk a little about those diffusing computations. Well, again, just to give an idea. The diffusing computation is a wonderful concept of driving a distributed computation in a network. What happens is that if you need to get an answer from your neighbors, and you don't want to compute it yourself all alone, you can ask your neighbors if they can help you. This is a very general schema, and EIGRP is just using it. So you can send your query to your neighbors, and your neighbors can either respond directly like the guy on the right, so he isn't really in any way influenced. He just gives you his answer and is fine. But if those neighbors, let's say on the top and bottom, if they don't have the answer immediately, they may need to go and ask themselves. So they will propagate the query themselves. And this will eventually end somewhere, at the worst case, at the very edge of the network when there is nobody else to ask. And then the replies will start coming back. But notice that till the router in the middle gets all the responses, it cannot make the final choice itself. So it means that a single router is dependent on the whole chain of routers waiting to each other to get all their replies, not just one, all, before you can start sending your own replies. This is, well, on one hand, this is a wonderful mechanism in EIGRP because it involves just those affected routers into recomputing the best path that are truly affected. Others, they don't care. They just send a reply right away. But at the same time, it makes them dependent on each other. So it's also an Achilles heel of EIGRP, sometimes ending in those SIA states, stuck inactive. It's of vital importance in EIGRP to limit the propagation of the queries as much as possible to limit the depth of the network that needs to be involved. And we have many tools to do that. We can have a feasible successor, of course, because if we have a feasible successor, we don't even ask. Or even if it is a non-feasible successor, and we ask him if that router has readily available backup path to the destination, it's just going to respond. It's not going to propagate the query itself. Assuming the query needs to be propagated, then the boundary can be also set by distribute lists, in which case the query stops one hop beyond the place where you place the distribute list. And that is because we don't really influence the queries by distribute lists. But if your neighbor doesn't know about a network since you filtered it out, when you ask it about it, it just says, I don't know, I've never heard about it. And that's it. So the query is stopped right there, one hop beyond the distribute list point. The same happens with summarization. That's the same thing. And summarization is a very powerful thing in EIGRP to limit the queries. And also, I may have stub neighbors which say, don't ask me, I don't know. That's why we have the stubs in the first place. Or if we hit an end of the network so that we have nobody to ask more, obviously. But that's actually the worst case, hitting the end of the network. If it happens that the query is running in the network, the diffusing computation is progressing but doesn't end in time, this is something we call stuck inactive situation. By default, it's 3 minutes. That can get extended to 6 minutes. If we use this extension to EIGRP, it is called the SIA rewrite, stuck inactive rewrite, or simply SIA query and SIA reply to ask a neighbor, hey, are you still working on my query? And he says, yes, I am. So I will extend the time given to him. The SIA conditions, stuck inactive conditions, typically manifest themselves like this. They say a route has been found stuck inactive, and now quite an unpleasant thing happens because we reset the adjacency to the neighbor fully, which ironically it may put even more instability into the network, so it actually can aggravate the situation. There are two aspects to a SIA condition, right? First of them is the route is stuck and the route is active. And we need to troubleshoot both. Why did the route become active in the first place, which is typically easier to find out? And why did the route remain stuck in the active, which is more important but also far more unpleasant to find? And there is no quick solution to this. This is what I already mentioned. The troubleshooting the active part of the SIAs means that we need to find out what has made them go active. Is there a flapping link? Is a router going down and up? Do we have a problem in exchanging the routes and flapping adjacencies? Is there maybe a router that is being connected to the network, injecting and then withdrawing the routes based on some local criteria and conditions? Simply, we need to find out what makes a route go active and not. The show IP EIGRP event can be helpful here because it can tell you what made it go active. Regarding the stuck part, this is more problematic. The fact is that the moment you have reported a SIA event, it has actually passed already, because we do not know or we don't measure what's the normal time for a query to take. We cannot inform you, hey, this is taking kind of long, but still we're on it. We just inform you, this has taken way too long, we have killed the session already. And once this is done, the traces are mostly gone. Event histories could be your help. If you are on the situation that is currently underway, that you are looking into an active SIA in progress, it's slightly easier. What you can do, this is a slightly contrived scenario here, in which case the network on the left has been disconnected. So router A, and in fact all routers are trying to find a replacement route, which doesn't really exist, but we don't care here. And the computation doesn't seem to be stopping. So let's see, what can we see here? Let's assume that RTRA is reporting a SIA issue or gets repeated. So I will be looking, where is a outstanding reply awaited? And RTA would say me, well, tell me, I'm waiting for router B to respond. Okay, let's move to B. B will say, yeah, I'm waiting for C. The R flag means I have queried and I'm still waiting for the reply to come back. Okay, let's check C. This starts getting more interesting because C is already telling me that C has sent a retry. Retry is 1, maybe more. And I also can see that there is this Q flag downstairs, RSQ, meaning that I've already sent a SIA query, stuck in active query. Now what happens? Let's see why D isn't responding to my queries. I do show IP EIGRP topology active, and we see, okay, there is no active route here. Well, how come? If I asked him, he either should be active, or if he responded, then I should have gotten the response back. Why I'm still waiting for it? Something strange here. Let's go back to C. It's still in the same state. Checking the EIGRP neighbor table here, we can see that we have an unacknowledged packet standing in the queue. D probably hasn't received. So going and doing a simple ping, oops, here's our problem. We have a broken unicast connectivity here. And if somebody asked, just how could this adjacency even come up? Remember, sometimes things broke in production while in operation. Something may have broken after the initial synchronization has taken place, and only afterwards your unicast connectivity may have broken because of whatever is happening on that link. Yeah, slightly contrived, but still possible. Then now the troubleshooting would go back to troubleshooting why we don't even exchange the routes here, or even the unicast packets here. What we can do is be very mindful that the EIGRP stuck in active is aggravated by excessive redundancy and deep depth of the network that we may have. Actually, let me move this link. We need to be mindful of better congested links that may aggravate the situation. We need to be mindful about MTU issues, especially if we are asking about the lots and lots of routes in the same query packet, because we can do that. Query range is 2D, which is the typical problem with EIGRP stuck in active states. And be mindful of excessive redundancy, as I said. 2 distribution switches, 100 SVIs, and you run EIGRP on all of them. It means that you have essentially 100 EIGRP adjacencies, and the query will be multiplied by 100 because you asked neighbor 100 times. Don't go for it. If you have a situation like this, you have distribution layer switches, multiple SVIs, make them passive. Dedicate just one link to carry EIGRP, or dedicate one VLAN for the EIGRP adjacency, but there is no point in running adjacencies across all your SVIs just because you are the distribution layer switches. Simplify, summarize, filter, and this is going to help. All right. Just finishing all this. There are 2 recommendations here. The first recommendation with the CSC DP 33034, this is actually very, very long overdue. This is a SIA query and SIA reply process that gives additional time to the neighboring router to respond. But if it's really a problem in the packets, it's unlikely to respond. So this is not going to solve your issue. What can make the impact less grave is using the soft SIA command. The difference is that without it, we'll break the adjacency completely. With soft SIA, I'm going just to resynchronize with the neighbor if possible, which is less impactful and less harmful for the rest of those networks that have not been impacted by the SIA state. All right. Any questions so far? Sir.
So I had a strange problem that happened. We changed the MTU.
Yes.
A number of our WAN links and stuff. The adjacency stayed up. Everything was fine. Months went by, and then we had that link go down and come back up, and we didn't have matched MTUs on both sides. And then we saw that exact problem, but it didn't show up right away when we changed the MTUs on one side.
Wonderful. What the gentleman mentioned is that they had a MTU mismatch on in their topology, but didn't notice at the time because the network was already stable. Then they had a flap, and then the problems with, I suppose, the synchronizing and CS states came in. As opposed to OSP or IS-IS, we do not advertise the MTU anywhere in the EIGRP packets, and we do not verify it. It goes just as silent data plane packet loss, which is so difficult to troubleshoot. Fully agreed on this one. All right. Let's check about a couple of possible issues with summarizing. Now, this is not really going to be a problem in EIGRP per se. This is more about the use of summary addresses that may backfire in certain situations. As you know, summarizing is a way of putting together multiple prefixes onto a prefix that is shorter, but describes all the address space in one go. Now, what EIGRP does when it summarizes the networks is that it has to assign a metric to the summary route as well. For the summary route, what we do is we take the cheapest component and copy its metrics into the summary route itself. So the summary is as cheap or as expensive as the most cheap component it was hidden under it. We do this also for RIP, for OSPF, and for ISIS. Well, actually, for ISIS, we don't. If the component of a summary route gets deleted, or if you learn about a new component of a summary route that you are hiding under the summary, because of this rule of keeping the summary as cheap as the cheapest component, you really recalculate the new cheapest metric and possibly re-advertise the very same summary just with the updated metric. And this is typically useless because unless you summarize on multiple points from a certain area, if you want to call it that way, then the metric of the summary has no meaning because it's never going to be compared to anything else. You just consume CPU cycles and advertise changed route that doesn't change in the next hop, it doesn't change in the prefix, it just changes in the metrics itself. Not useful. What we can do with the recent code, and this is implemented in the named mode, is to use the summary address command that will also allow you to specify the metric manually in those typical metric components: bandwidth, delay, reliability, load, and MTU, which we're not using, but it's still being advertised. This will decrease the churn in the router's topology table that performs the summarization and also anywhere else, especially for DMVPN implementations or for implementations where you summarize lots of routes, advertise them somewhere else. Might be something to consider because this is going to decrease your CPU load and this is going to also make the rest of your network silent since it doesn't care about those useless updates anywhere. Dual-homed situations with, let's say, remote locations or stubs where you want to advertise just a default route are kind of creative problem for EIGRP. What is typically done in these situations, if you take the routers A and B as the, let's say, the headquarters site, is that we summarize into a default route. That's perfect. So router C will only receive a default route itself, nothing else. And that's totally enough. But the routers A and B themselves may be getting their own default route learned from some kind of an internet-facing router, and again, through EIGRP. Now, what typically happens is that because we summarize into default route on A and B, we also create this discard route pointing to null zero to prevent routing loops. And discard route has an administrative distance of 5, which is very good. Meaning that neither EIGRP itself, not even BGP can override it because 5 is so good. So what happens is that if you summarize like this, those routers A and B cannot really learn the default route on themselves unless it's configured statically or something. So you actually cut them off. What needs to be done in this case is define the administrative distance on the summary route itself. And this can be done, for example, with IP summary address, and then the administrative distance, for example, 200. And this works very nice as long as routers A and B learn the default route themselves. But, okay, now this is just how the C would look like, because now A and B are both advertising the default route, are summarizing very nicely, and they are sending the default route down to C. So C will have two routes, so two default routes, two next hops. But what happens if A loses a path to internet? A gets disconnected. What now? Well, since A doesn't longer have the external route, it creates the local summary route and advertises it. And if the original one happened to be external, because we typically do redistribute all zeros into EIGRP, and so it gets advertised down. Since A doesn't have the external route from the top router itself, it's going to advertise its own summary, which is going to be internal with an administrative distance of 90, and this will take over on the router C, because router C sees internal through A, which leads nowhere, and B, and through B, which is external, so not as preferred. So C will converge only on A, and A is black holed. So we have a problem. Again, what can we do here? Yeah, this is just the output. One of the possibilities is to advertise, actually configure the summarization with an administrative distance of 255. This has a very peculiar effect. If you summarize into a summary network with an administrative distance of 255, you will not advertise that summary. You will advertise that network equal to the summary only if you learn it from elsewhere. But you're not going to advertise it if it's originated by you lonesome. Meaning, if A learns the default route, it will propagate it. If it doesn't learn the default route, it won't propagate it, but since it's a summarization, it won't advertise also anything else. So the summarization still holds as a filtering tool, but it only will pass the default route down here, and only if it's learned dynamically by A and B itself. So let me complete the scenario here. Yeah, there is a comment here. Don't use the 255 for single-homed routers. If C was single-homed, keep in mind that the default route stands only not for internet, but also for the rest of the networks on your headquarters or on your other locations, right? Because you summarize everything into the default route. So you have to be advertising the default route no matter what. Otherwise, you cut yourself not only from the internet, you cut yourself also from the rest of your network. Just to complete this, another solution would be here to use the summary admin distance that for, let me just complete the configuration here. So what we can do is, instead of summarization, use a distribute list and allow only the default route to be advertised. Don't use the summarization. And at the same time, set up floating statics on router C that would be higher than the EIGRP learned one. The idea is that if you, as a router A, learn a default route, you send it. You don't send anything else. If you don't learn it, you don't send it. As far as good. If none of routers A and B learn the default route and none of them sends it, then router C will simply statically point up there to the A and B, because the default route still stands for the connectivity to the rest of company network, not just the internet. That's why the floating statics are there. But as long as you learn the default route, you will be pointing to that router who advertises either A or B or both. That's the idea here. All right. Specific problems may also occur in this network. It's not that unexpected here. Imagine that routers A and B, let's say DMVPN hubs, and they are connected on a common LAN network inside your headquarters. Both of them are configured to summarize all the spokes into a couple of nice summaries here. Router X can send packets to a specific location through either router A or router B. And this typically doesn't matter because the packets hit their end. And if you don't have stateful firewalls here, and you don't practically care. This will still work nicely. What's the problem here is that if I break the link between A and C, router A stops advertising the reachability to the network that is located at the top, the 10.1.1.0. I don't have it. A is not connected to it, so it cannot advertise it. Remember, because of the summarization, it still has the discard route for 10.1/16 or something. The only real path to reach the network on router C is through B. But A doesn't know, because both A and B advertise only the the summary routes through the common network between A, X, and Y. A has no way of knowing that there is a backup to the router C and whatever is behind. So in this case, if router X, because of the equal cost multipath, decided to use router A to reach that network, it would black hole the traffic. If it decided to go through B, it would work nicely. How to fix this? There is just a very simple, although maybe slightly pathetic solution. We need to create a new link somehow between A and B that will carry those routes unsummarized. And it can be a dedicated interface, which would probably be a waste of resources. It can be a new VLAN, which you can always create. It can be even a GRE tunnel just hooked on the IP addresses on the common network on A, X, and B to make sure that it really talks through the company network and not through the spokes. You simply need to have an extra link between those two routers that allows EIGRP to exchange unsummarized details, in which case A can understand that it can still reach the spokes through B, which it didn't understand so far because of the summary. So this would be the approach here. All right. Moving on. Redistribution and problems with redistribution. Just a couple of notes here, because I suppose many of you have been facing redistribution in the past, so you know what gotchas are here to be expected. EIGRP is not going to invent metrics when you do redistribution. EIGRP relies on you to specify them parameter by parameter, especially when you redistribute from a different protocol. So just a very pathetic example here, if you redistribute from RIP, then on B and C you would not see that route because you didn't specify any starting seed metric. You need to enter something. Now there are certain exceptions here. If you want to show off and remember all of them, be my guest, but in my personal opinion, unless you are running MPLS L3 VPNs, in which case you know that the EIGRP metrics are carried in BGP and can be reconstituted, it's always better to specify the redistribution metrics by you directly, because that's what gives you the safety and the knowingness of what is going to be used as the redistribution value. Be mindful of this type of lazy type of redistribution configuration. And we see that quite often. When you do this, redistribute whatever metric and all ones because it's so easy and so fast to do, you will end up with a very high initial metric. And keep in mind, this is still distance vector. The metric has to have a space to grow somewhere, but if it hits the infinity, it's undistinguishable from a poisoned route. It will be understood as unreachable. And just a question, what is being used as the indication of infinity in EIGRP? Anybody knows? Listening? That's right, but since we have it all split into bandwidth and delay and reliability, where would this indication be put? Because we never carry the overall number in EIGRP. We always have it advertised as a split part. And this number will be put into one of the components. Which one? It's here. Delay. It's going to be delay. Anytime you see the delay set to all f's, that's infinity. Delay set to all f's is infinity. Be careful of this. It can bite you. What I typically recommend is using, well, unless you have multiple redistribution points, it doesn't make really sense to try to be extremely careful. So just be reasonable, and using a redistribution metric typical of, let's say, 1 or 10 gigabit per second is going to give you ample space to grow and still have the metric representative of something. Another surprise that you may actually been hit by in the past is that you did a configuration like this, router EIGRP1, you did network, just a network and nothing with redistribution, and somehow a directly connected route made it into EIGRP and even said, hey, I'm redistributed. Why is this? Well, in iOS, if you define a static route that just points out an interface, doesn't use a next hop, it's treated as a directly connected. Actually, even if you do show IP route, it will say S as static, of course, because it's static, but then it continues says it's directly connected. So it's actually both. And since the network commands applies to directly connected routes, EIGRP simply obey and inject that route into EIGRP. And this is what's going to happen. It's not going to happen with routes that have both the next hop and the output interface specified, because the next hop is already there, so it's no longer a directly connected route. This has been a source of confusion, saying that if you do network all zeros, you will advertise a default route in EIGRP. No, you won't. It worked only because typically those customer has IP route all zeros, dialer 0, or even Ethernet 00, but never point out a static route just out of Ethernet. Yes, sir. Okay. Not a feasible successor. So don't be surprised by this. It's not a bug. I don't know if it's a feature, but it's just what it is. Team, you know about the problems in mutual redistribution. Do I need to go with you over preventing routing loops in mutual redistribution on multiple points? Who would like me to go through this? A couple of people. Okay. Thank those guys. Okay. There you have it, David. Okay. So what do you need to be careful about? With redistribution between two routing protocols, you are losing the details about the origin, and you are losing the details about the initial metric. That's why it's possible to feed an information back into the protocol where it all started, and because you have full control during the redistribution over the resulting metric, it's not increasing anymore. You are overriding it. You can make it suddenly even more feasible, so to say, or more usable, more interesting than the original path, and lure the original protocol into believing the path that has made it all across the world and feeds back into itself. Now, this is not going to happen in EIGRP if the initial route is internal. Why? Because if you take the internal route, then move it through another protocol and move it back into EIGRP, you will have an internal origin and an external duplicate. And EIGRP is always going to trust the internal one. But what if the original network was already external in EIGRP? Then you move it through the different protocol, then you feed it back into EIGRP, and then you have a problem, because you have those two undistinguishable sources of external information. So this is where you can be hit, and this goes both also for OSP, about focusing on EIGRP now here. So what can happen here, depending on how we set the metrics, if the original route has been already external and is being fed back into EIGRP with a better metric than the original external one, we may end up with having a loop. We may. What we need to do to prevent this? The best prevention is simply not to feed the routes back where they came from. This has always to be prevented. How to do this? We have technically a couple of options. We can, okay, one directional redistribution is one of the possibilities, but sometimes it's not feasible because you may need a bidirectional redistribution, since you need to know, both protocols need to know about the same thing. Then you can do filtering based on the prefixes themselves, but this is very tedious because any moment you redistribute a new prefix, you also need to add it to this filter that prevents it from being redistributed back. So the easiest way of doing that is using tags. Before I go on the tags, there was a gentleman who I believe wanted to ask something. Any question? Yes. I'm sorry, you need to tell me. There was a comment, we can also modify the administrative distance to prevent a loop. That is correct, but this goes back to the per-prefix manipulation. I can modify the whole administrative distance of the whole protocol, but this is typically not preventing me from the routing. Okay, it's not a good task because I'm then changing the behavior of the whole protocol for all routes, not just the ones that are redistributed. So if I change the protocol as a whole, it may also have consequences I did not want to have. I can change the administrative distance based only on the prefix itself and potentially the next hop, but it requires me to list them all. So in terms of listing all the possibilities, thank you, absolutely correct. Modifying the administrative distance is yet another way to do this, but it's as tedious as filtering them one by one. But if it's just a couple, by all means, it works perfectly fine. Thank you. Regarding the tags, well, the idea is that the moment we take a route from one protocol to another, we first check if the route has a certain number defined by me attached to it. We call it a tag. It doesn't have any meaning to the protocol, it has meaning to me. If the route has this tag defined by me, I will deny it because I know I am adding it. It's not done by protocol automatically. I will add it myself. So any routes that will already have the tag that I'm looking for, I'm simply going not to redistribute them. All the rest will get that very tag I'm looking for. And this is done using a route map, which is on the top, called use tags. In the first section, we simply search for the tag on the route. Does it have the tag of the value of 1,000? Okay, if it does, I'm not going to take it because the action in the heading of this section of the route map use tag says deny 10. Any route that will have this tag will be denied. And all the rest of the routes which did not have the tag and so have passed it to the second section of the route map, yeah, I will add the tag to them. And now the redistribution will simply use this route map, looking and sifting through all the routes taken from one protocol, denying the ones that are already tagged, and tagging the rest. This approach allows me to be very general because I do not need to go through prefixes individually, and it's adapting to whatever you redistribute in the future. Easily done, easily implemented. This is how it will be used. Sometimes I also use use different tags depending on what protocol they are redistributing from, just to know where it came from, because with this 1,000, you cannot really know if it came from OSP or from EIGRP. That's totally up to you. All right. Now the redistribution will be prevented here. With regards to additional propagation problems, as we close to the conclusion, I've already mentioned the problems with zero successors. Now with zero successors, once again, those are the routes that didn't make it into your routing table because something else, something better was in the routing table already. We cannot advertise those routes because we're not using them as EIGRP ourselves. So if those routes shall be advertised, you simply need to make sure that the conflicting or the offending route is not in your routing table. Why did it get there? You need to find out actually. That may depend on your local configuration and may actually be needed. But remember, there is no way for EIGRP to advertise a route that it is not using itself, because if we did, we would lose the loop prevention, and we cannot do that. So this would be the zero success route. What can be slightly confusing that aside from conflicting routes, let's say from BGP and EIGRP, we may also see certain situations where you run two EIGRP processes on the same box and in the same VRF with two different process IDs, two different ACE numbers, and both of these EIGRP processes knowing about the very same route. It's not allowed for the EIGRP to install a route into the routing table from two processes. The first one wins, and it's totally a race condition. Depends on the timing. So the first process wins, the second loses, even if they have the same administrative distance. And the second process will not be able to advertise the route anymore. Keep this in mind if you do run multiple EIGRP processes and they happen to be running and learning the same set of networks. They will fight themselves out from the routing table. The duplicate router ID is somewhat of an obscure thing. Initially, we have advertised router ID. You may know that EIGRP actually has a router ID, but nobody talks about it. And it's selected the same way as OSPF. You can manually set it up, or you copy it from the highest loopback, or the highest IP on the loopback. And if there's no loopbacks, you will just copy it from the highest IP on the live interface. EIGRP originally used the router IDs for redistributed routes as an additional check to prevent routing loops for external networks. And the idea was that for a redistributed network, the router performing the redistribution would sign itself in the update by its own router ID. And if that update ever came back to it again, then on top of all the feasibility condition checks, we'll still check if the router ID is there and just deny the route if it saw its own router ID there. Since certain version, when we changed the TLV format of EIGRP update packets with wide metrics, we also started advertising the router ID for all routes, not just external, but also for internal. And unfortunately, we didn't tell you. What this means is that if you do some kind of migration in the network, you replace one router with another, and typically this happens like, you configure the new router exactly as the old one. You prime it with a configuration, maybe different IP addresses, but have it very similar. Typically, the router ID would be duplicated. Then you put the router into the network, let it come up, deactivate or switch off the old one. You may have a problem in that the two routers will ignore their routes mutually because they will see them mutually advertising the same router ID. And I'm not talking just about external networks, I'm talking about all networks. How can you see this, or where you can see this? Well, it's not going to be in the logs anywhere. We don't advertise it as opposed to OSP, for example, that barks on you when there's a duplicate router ID. What you would typically see if you went enough into the logs, show IP EIGRP event, if you're lucky, you will see that for a certain route, there will be a duplicate router ID advertised. A duplicate router ID that tells, hey, we may have a problem here. And this change was introduced with the EIGRP release number 5. By the way, current is 28, so we've gone pretty far since then. So if you are using an EIGRP version of this, and if you do show IP EIGRP topology and then check out the particular network, you will see that the router ID is indicated there. Be mindful of this. We do not log the conflicts, but they may still be there. Make sure that your EIGRP routers also have unique router IDs. So make at least using unique loopback IDs a habit. OK. This is what I commented, just how the EIGRP picks the router ID, so I'm going to skip this one. OK, final 15 minutes. Any questions so far? Pardon me. All right. A couple of specific features here, specific functions. As I mentioned already, EIGRP is going to consume up to 50% of the bandwidth on the interface, so be mindful that the bandwidth setting itself should be reasonable. What I ask you, and again, and there is not, I cannot emphasize it enough, do not use bandwidth as a means to make a path more or less favored. Use delay for this purpose. Don't try to get smart with bandwidth, because EIGRP typically outsmarts you in a very bad way. With multi-point interfaces such as DMVPN, there is another set of challenges, because as you know, EIGRP is not going to take the percentage of the bandwidth as specified on the configuration, but it also tries to pace the packets divided by the number of neighbors it sees on the interface, so that the traffic of the interface is not oversubscribed, but it also means that we're slowing down the communication with each and every individual neighbor on such a network. If you need to tweak stuff and settings and QoS, again, do not do bandwidth histrionics on such an interface. Much better is to use the DMVPN per QoS, per tunnel QoS feature that allows you to specify QoS parameters for individual neighbors as they come back and register to you, and then you associate class maps and policy maps with them. This is better to do if you need to do any kind of per tunnel, per neighbor QoS modification. This would be the way to go. Again, keep the bandwidth at the realistic level and do all the remaining stuff using the DMVPN per tunnel QoS feature. Since DMVPN involves rather a large stack of additional technologies, because we need to use NHRP for resolution, we need to use IP for multicast and broadcast replication, since the underlay is not assumed to be multicast enabled, there's a lot of resources that get depleted when there is a heavy communication in EIGRP or in multicast in general, because we need to emulate multicasting on the IP and NHRP level. And so with a large of communication in these types of networks, lots of other resources may get trained, not just EIGRP. I'm talking about packet buffers, I'm talking about NHRP tables, I'm talking about physical buffers, because they will get, every single multicast packet will be replicated n times for n neighbors that you might have. The commands that may be useful here to just see what's happening on the NHRP side of things would be, for example, show EIGRP traffic, where you can see just the numbers of the hellos, updates, queries, replies, and so on. Again, a good command for you to keep track of the intensity of the communication and even of the statistics and the types of packets being received and sent on a certain overall for your process. And as I've said, since the DMVPN involves so many additional technologies, typically if you do run DMVPN, do run EIGRP over DMVPN, then these commands here are your friends. And if you see, this is not just HSRP, but this is also packet buffers, interface buffers, and of course, EIGRP specifics as well. Once again, keep in mind, with all non-broadcast multi-access technologies such as DMVPN, we do head-end replication of the multicast that in itself adds a strain to the router. Regarding problems with links larger than 1 gig, you know where I'm going to about wide metrics. The idea is that EIGRP was designed in times when fast Ethernet was considered fast. And all the metrics are tuned to the idea that, let's say, fast Ethernet with 100 meg is already fine, 1 gig is super, and 10 gig is, man, that's wonderful. Nowadays, 10 gig on Nexuses is the minimum, and we have switches, I believe, that go up to 400 gigabits per second, recently announced, and EIGRP cannot make any difference between these fast links. The bandwidth itself is computed as how many times your link is slower than a 10 gig link. This is what we do in EIGRP. That's the classic metrics. If the link is 10 gig or more, you cannot tell them apart because they all end up in the same number. Yeah, you could theoretically end up in a metric or the bandwidth component of the metric even being 0 if you divide the 10 gig by something more than 10 gig. Now the code isn't, fortunately, that stupid as to use the metric of 0 in the computations, but still it cannot really distinguish between the faster and the slower link. And this is how it will look like. For a port channel that consists of two 10 gig links, yeah, the minimum bandwidth would appear to be 0. Yeah, it really doesn't tell you anything really about the usable thing. Also, we have this delay parameter. Whatever is being told to you about the delay is just a number. It doesn't really have any sensible meaning. It was tried to approximate the delays on interface of a certain speed, a serialization delay, but it's really just a number. EIGRP just taps into iOS core code, and iOS core code has these delays hardwired. There's no way we can modify them on for faster interfaces. Since they are simply there, nobody's going to touch the code. So again, for 10 gig interfaces or more, we don't change them. Or even, 10 gig and more. The delay is 10 microseconds, so we can't really distinguish between the two. What this is going to, you may use EIGRP on links that are 10 gig and faster. It's just not going to treat them any way differently. It's just going to treat them all along the same. So in a network like this, where you have a couple of 10 gigs, just a couple of more hops, EIGRP is not going to understand this. It's just going to take the shortest path because it simply sums fewer links together. Starting, OK, I'm not going to talk about this, how to solve this, because everybody knows. Go around and change your delay statically. Yeah, sure. And everybody's going just to jump to the roof, because in a network with so many links, you will have just too many problems tuning this normally. What we have done in EIGRP release 8 and further is that we have enabled what we called wide metrics. Wide metrics is a feature that expands quite drastically the space and the granularity of the metrics that we do. We can go theoretically up to 4.2 terabits. In fact, we can do even more, but since the iOS infrastructure only reports the bandwidth as a 32-bit number, the real bandwidth that we can really advertise is 4.2 terabits. And we can go in delays in resolutions of picoseconds. Now, again, this is almost touching the physical limits, right? But this is the range that we can allow ourselves to work with by moving into 64-bit metrics. The moment you are running EIGRP release 8 or more, you have the wide metrics in your box. You do not touch it, you do not configure it, you don't tune it, it's just there. And how do you know? Well, the moment you do show EIGRP, and this is the new command, show EIGRP address family IPv4 topology, but it would also work with normal show IP EIGRP topology. The moment you see the metrics being indicated in picoseconds, the moment you see this indication here, not sure if my pointer is visible, rib is 2048. This is an indication for you that you are locally running these wide metrics. If you connect a new neighbor to an old one, they will detect these facts. And for the old neighbor, we will use the old metrics, but we will need to recompute them. But this change is backward compatible in that we know that some neighbors may be old, some neighbors may be new, and we adapt to their capabilities. Be mindful of one thing, though. And I'm just going to display all the output here. When we talk from a new neighbor to an old neighbor, we will be facing a certain change in the custom metrics, right? If both R1 and R2 have been running the old release, let's say release 6, with just the classic metrics, the composite metric for a route would have been, for example, the 307200. If I migrate router 1 to a router that speaks the new metrics, then because of the need to recompute them and express them in the way we do in the old metrics, what the router 2 that hasn't changed will see might be slightly different. Because of the recomputation, I would need to go into the maths that's stuck behind the thing, and it's not really useful. Why this is necessary to know? if you are using offset lists and you have them tuned for specific offsets, you may need to reevaluate them to see if they move your metric just the way and just the amount you need. And again, this applies only to those migration scenarios where you face old routers and new routers together. For new ones, it's obviously not a problem. But for new, speaking to the old one, there may be some round of errors introduced that you may need to take into account. This has been in EIGRP for at least 5 years, so if you run any recent code, you won't be facing this. But we know that I've seen catalysts running, not only running iOS that was 10 years old, the uptime was 10 years old. So, yeah, you don't get this NX-OS, right? But that's a different story. So, to conclude, EIGRP, in my opinion, is still a state-of-the-art protocol because truly, I'm not going to go into flame war between distance vectors and link states. There is an application for both of them. And EIGRP truly is a state-of-the-art protocol because it is fast, loop-free, and has a number of features simply not anywhere else. Of course, it depends on the actual implementation if it really suits your network and your needs. However, we do have a set of tools that we have in our iOS or NX-OS or even iOS-XR that allows you to see into it, and hopefully this session has helped at least a little to dispel some of the myths that have been there. This being said, please allow me to do some shameless marketing. 4 books that have been done and written a couple of years ago, but still they're out there. Is there actually any demand for an updated EIGRP book here? Would anybody be interested in if a new EIGRP book came out? Okay. I'll try to talk to Don and Donnie to see if they would be willing. Remember, EIGRP has become open a couple of years ago, so whoever other vendor tells you it's not, it's closed. It's not. Just one request, 2. Please keep engaged, and if you do have any questions, do come back and ask us in the Spark room for anything you might be interested in. It's going to be up there for a couple of weeks to come. And although I'm not going to click there is, as you know, a survey after every and each session. The only thing I ask for is a candid feedback. Thank you.